All right, here is my work solution to the problem that asks where the Earth's gravitational field and the Moon's gravitational field will cancel each other out. So let's take a look. So the first thing I've done here is just set up a diagram showing the Earth on the left, the Moon on the right, and the distance between the Earth and the Moon shown there. What I'm going to do, just to give us a bit of a better understanding of what the question's asking, just to hopefully illustrate it in case it's not clear, is on top of this little diagram I've got, I'm going to overlay a graph of the gravitational field strength of the Earth. So we can see that dotted line running down to the surface of the Earth. So at the surface of the Earth, the gravitational field strength is 9.8 newtons per kilo, and we can see it drops off as we move further away. The Moon will do something very similar. G at the surface of the Moon is 1.6, and then it will drop away. We can see where these two graphs overlap would be where, at that exact location, the G that the Earth is trying to pull the object to the left would be equal to the G with which the Moon would be trying to pull the object to the right. This point can be called a null point, that the overall value of G, or the net G at that point, would be 0. And it is the null point that this question is asking about. Where is it? So just before we move on to calculating it, if we dropped an astronaut just on the Earth side of this null point and just released them, they would accelerate towards the center of the Earth. So if you made it if you were just on the left of the null point, you would need no propulsion at all to get back to Earth. Of course, if we just dropped you out there and released you, you would come crashing to Earth very, very quickly. But that's a whole different issue. So let's go about solving this. So at the null point, we know the gravitational field strength due to the Earth at that distance is equal to the gravitational field strength due to the Moon at that other distance. So we can solve these two or put these two expressions together simultaneously. So on the left-hand side, we have, for the Earth, we've got gm, mass of the Earth, over our radius from the center of the Earth squared. And on the right, we've got gm, mass of the Moon, divided by our distance from the center of the Moon squared. Okay, we can see that our g's could cancel out nicely, and we know the mass of the Earth and the mass of the Moon, but that leaves us with two unknown values. This really fundamentally is the problem with this problem, is that as we lay it out here, we have two unknown distances. So what we will do, and this is the key, absolute key to being able to solve this problem, is change the expression for the distance from the center of the Moon to the null point. Instead of being r Moon, we could say, well, it's that total distance from the Earth to the Moon minus our RE, our distance from the Earth. So this new expression here, the radius from the Moon, will be equal to 3.8 by 10 to the 8 minus the radius from the Earth. So now our two R values are the same. So we substitute this expression in. This is just, we're sort of recapping the maths here. So from that first expression, we can cancel our g's, and then we're left with the second expression, and then we can square root the top and bottom of both fractions, as well as, this is where I've put in my new expression for the radius or the distance from the Moon, 3.8 by 10 to the 8 minus r Earth. So we do that, and the bottom line there, or the bottom equation, gives me the square rooted values for the mass of the Earth and the mass of the Moon. So I've already gone ahead and substituted those values in, those two masses in, and square rooted them, which means I've got rid of my squared on my both of my distances on the bottom of the fraction. Continuing on, so I've just brought that last expression across. Then I have multiplied both sides by 3 by 10 to the 8 minus r Earth to get rid of the fraction on the right-hand side. And so that gives me a new expression on the top left. And then I want to get rid of the fraction on the left-hand side, so I multiply both sides by r Earth. And then I am left with 9.31 by 10 to the 20 minus 2.45 by 10 to the 12 r Earths equals 2.7 by 10 to the 11 r Earths. So let's add 2.45 by 10 to the 12 r Earths to both sides. We simplify it down to 9.31 by 10 to the 20 equals 2.72 by 10 to the 12 r Earths. We divide both sides by 2.72 by 10 to the 12, and we find that r Earth, or our distance from the centre of the Earth, is 3.42 by 10 to the 8 metres. And I've just substituted that value, that distance, into our diagram to show what that distance represents. And we can see that it is most of the way to the Moon. That whole distance is 3.8 by 10 to the 8. The distance to get to the null point is 3.42 by 10 to the 8. So most of the way from the Earth to the Moon, you are going towards that null point. I hope that helps.